Okay, this is part 3 of this run through. In part 1, I went through some multiple choice questions, and I also went through core practical 1, which was this question. In part 2, I went through core practical 3, which was on internal resistance. Yeah. And now I'm going to go through some slightly different questions, which I've called Section C. You'll notice that I've handwritten Section C. And because my students are doing the Edexcel linear, I'm making it in a style of the linear paper, but I've actually used mostly modular questions. So practical skills and thinking skills, if you like, come into Section C. So I've chosen a thermistor question because you'll see that it's got a lot of practical skills in it. So let's go straight into it. A student investigated the behavior of a thermistor using the circuit diagram shown. So you can see this, the thermistor is the one with the voltmeter across it. She heated the thermistor to 100 degrees centigrade. How? And measured the potential difference across it. She decreased the temperature and recorded corresponding measurements of voltage. Okay? So she took the measurements of temperature and voltage until the temperature reached 10 degrees centigrade. Well, where we are, room temperature will be 20 something degrees usually, and most places it will be the same. Yes, whether you've got to use heating or cooling, as we do, the room temperature will be 20 something degrees. So to get to 10 degrees, you will need to use ice-water mixture. So describe how the student could vary the temperature of the thermistor for this investigation. Well, thermistors can actually be immersed in water, and this is one of the practicals that is suggested. It's not a core practical in year 13 when we're doing thermal physics. So we do link year 12 with year 13 with a similar kind of calibration exercise to see how temperature affects the resistance of a thermistor, because it is basically a temperature dependent resistor. So initially you would need to use something like a water bath. What I would just use a kettle to boil water and plonk the thermistor, not all the wires, just the thermistor part of the circuit, into the boiling water, 100 degrees centigrade. And I basically take the voltmeter reading while the thermistor is immersed into the hot water. Okay? There are different types of thermistor you can buy. So 1 mark for realizing that what you would need to start with, because it's only 2 marks. So I would start with the kettle, a beaker, and allow that to be the starting point. Okay? It will be difficult to maintain it at 100 degrees centigrade, but as long as you got it, it's only 2 marks. The method would then be starting with the water at 100 degrees centigrade. That will be that part. And then I would allow the temperature of the water to cool while taking the values, but they want you to describe how the student could vary the temperature right down to 10 degrees centigrade. So you take the values at regular intervals, obviously maybe every 10 degrees centigrade, and you can actually speed up the experiment by adding some cooler water to the water and just take a variety of readings to get enough data points to plot a good graph. And then to get to 10 degrees centigrade, you would then need to use some ice to get it below room temperature, because obviously tap water will be around 20 degrees centigrade. Okay, so that's how you get 2 marks. 1, a general method, if starting with a hot water bath or something. I don't know, I don't really use hot water baths. Do they go up to 100 degrees centigrade? I would have to ask my technicians, because I see biology students using it more than physics students. The photograph then below shows a steady reading on the voltmeter, which is reading 6.85 volts in this picture. Okay, when the thermistor was at room temperature. So this is the room temperature voltage. Okay, and remember the resolution of a voltmeter is 0.01 volts. And what they want you to do here is to calculate the percentage uncertainty of this reading. Now, I was explaining to my students that percentage uncertainty is equal to half the resolution divided by the voltage value, or the mean value if you've taken more than one. So 0.01 is the resolution. So you want to use half of that value. So that will be 0.005 divided by 6.85 multiplied by 100, which will give you 0.073% to two significant figures. But usually with uncertainties, we round them to one significant figure. Okay, and this is taken from a practical exam question, which in IAL is called Unit 3, and it's not from January 21, it's from October 21, okay? If you want to find the exact paper. So that's how you do percentage uncertainty if you only have one value. The student then plotted the data points shown on this graph, for measurements of voltage and temperature. Okay, so voltage on the y-axis, and then I joined what I've called the curve of best fit. I then extrapolated here, and that's my purple pen, and my purple pen could go as high as 8.7. I said 8.6 is probably more accurate, and if you join the last 3 points, as you see over here, I've done in green, the minimum will be 8.4, okay? So somewhere around between 8.4 and 8.6, I think is probably the best value. So estimate the value of V for 0 degrees centigrade, which is what I've done. So I'm saying any value between 8.4 and 8.7 should be correct based on my curve of best fit. They've called it the line of best fit. And you'll see that the examiner wouldn't accept my value of 8.7 volts. But I don't think my curve of best fit is bad. Yes, I can see it's going a little bit badly drawn towards the upper end, yes, where I'm going to show you again in yellow, this purple line probably has gone a little bit too high, which is why I'm saying 8.6 is probably more accurate than 8.7. Okay, so it wouldn't be accepted, 8.7. So once we do it, once we've done that part, it says calculate the resistance of the thermistor at 0 degrees centigrade. So what's the resistance at 0 degrees centigrade? Well, the examiner's taken the 8.4 volt value, yes, and the mark scheme. So the voltage at 4.7 of the 4.7 K means if at 0 degrees centigrade the thermistor here gets 8.4 volts, the rest of the 12 volts minus 8.4 volts at 0 degrees centigrade, well then the rest of it will be equal to 3.6 volts, and that will be the voltage across a 4.7 kilo ohm resistor. Okay, so 3.6 volts will be what's the share of the 4.7 kilo ohm resistor, which is in series with the thermistor. Okay, so that's how we get this value, and it's basically the voltage sharing law, which is called Kirchhoff's second law. So once you know that, you can work out the current in the circuit, because you know the resistance of the fixed resistor is given to us in the question as 4,700 ohms, 4.7 kilo ohms, and that means you know the current. Once you know the current, they want you to work out the resistance of the thermistor, and we know the voltage of the thermistor. Now we know the current through both resistors because it's in series. You can then work out the resistance by dividing the voltage at 0 degrees centigrade, which we decided we'll use the 8.4 volt value, or whichever value you use, they'll give you credit for your working out, and it'll come to 1.1 times 10 to the 4 ohms. Yes, if you use the 8.4 volt value, and that's to two significant figures at 0 degrees centigrade, and that you should put in here with the units. Never forget the units. So again, this is a continuation of a practical skill that you need, and you can see that they can give you a practical skill from potential dividers, which is not a core practical. Okay? So there's the mark scheme. I'll let you stop and have a look at how they did it. I think 8.6 is too low for some curves of best fit. I think you should be able to go to higher than that. Why they get 8.2, I don't really know. Okay, I would say the minimum should be 8.4. Okay, so I would say it should be 8.4 to 8.6, and there is how we worked out the final part that I just went through. Okay, so that's a good application of physics question. It also brings in practical skills, which is good. And then finally, here's part D, which we haven't done yet. Same question, 11 marks in total. And it says the student suggested that V, the voltage, is inversely proportional to the temperature. Yes? So is it? Well, if it is, then Vt will be a constant. Yeah? If it's inversely proportional. But they're saying in Kelvin. So that from a GCSE, you need to know that at 0 degrees centigrade, the temperature in Kelvin is 273. We know the voltage value at 0 degrees, 8.4 volts. Multiply that by the temperature in Kelvin, you'll get 2,290 volt kelvins. Yes? Then you could try it at 30 degrees centigrade and at 60 degrees centigrade to try it at different values. And again, make sure you've worked out the Kelvin correctly from your GCSE knowledge. Again, for 60, another 30 added to the 273 twice. And each time you do it, you can see the value is going down. So therefore, temperature is not inversely proportional to the voltage. So the student is incorrect. Okay, so as long as you do 2 or more values, you should be able to get the conclusion that the student is not correct. Okay, and that's how you get the final 2 marks. And here is the mark scheme for that. Okay, see, at least 2 pairs. I did 3 pairs, yes, and they come out to different values, not even close. Okay, so here's the final question. So I'm going to do section C all in one go. So it's going to be slightly longer than the previous 2 parts. Solar panels generate electricity. We know that from GCSE. When sunlight is instant on the surface of the panel. Obviously, it depends on the angle that the sunlight hits the solar panel, but this question doesn't go into that level of detail for it. It says the total generation of electricity worldwide in the year 2014 was approximately 23,800 terawatt hours. And 1 terawatt hour, yes, remember it's power times time. And instead of using watts and seconds, they're using terawatts and hours, and they're telling you, well, quite simply, that's just a certain number of joules. Now, if you remember in GCSE, a kilowatt hour is the unit they charge you electricity for. It's called 1 unit of charge. Okay, so this is part of the exam where they expect you to just be able to problem solve. Okay, so this is why I wanted to include this section in this first progress test for my students as we finished the first half term. Okay, so it says some scientists claim that if the Sahara Desert were covered with solar panels, you could just get enough energy, electricity, generated to supply the whole world. Well, we're assuming they're talking about the 2014 value. Remember this exam, most of the questions I got were from 2020. So you've got to calculate the maximum energy received by the solar panels in 1 hour, obviously in the Sahara, yes? The maximum intensity of solar radiation at the Earth's surface, it says, is 1100 watts per square meter, okay? So I just showed my students that intensity is basically watts per square meter, and it's given to you here. So they want you to use this value, and the area of the Sahara Desert is given in meters squared in standard form. So if we know it's 1100 watts per square meter, and you know the square meterage, yes, you can work out the total amount of power that is hitting the Earth at the Sahara, okay? Well, we're assuming that the Sahara is near the maximum. So there are assumptions in this question. So remember that you're going to have to use energy is power times time. And you know that power is intensity times area. If you change that equation round, multiply the intensity per square meter by the area, and you'll get this simplification of units. So you'll get the power for the whole area of the Sahara as this many watts. Well, you can already see that this many watts, yeah, is quite a lot, 10 to the 16. So there you want to change that. That's watts is joules per second. You want to get it for a whole day. Is that right? 3,000 for a whole hour, sorry. Multiply by 60 by 60. So in 1 hour, you're going to multiply that value by another 3,600 to get it in 1 hour. You're going to get this much energy. Because remember, over here, we want to go into joules. Okay? So this allows us to go from watts using the energy to power combination or calculation. You can now get it for 3,600 seconds. So that's how much you will get in 1 hour. Okay? So then, because that's what they want us to work out. What is the power, the energy received in 1 hour? So I should have stressed that before. Okay? And this is how much it gives you. Two significant figures. Remember, this is a lot of assumptions made here, so you can't really quote it too accurately. So 2 significant figures is sufficient. It then says, determine whether covering the Sahara Desert would be able to generate enough electricity for the whole world. Remember, they've given us the whole world value for 2014. So if you use the average day length to be 12 hours, yes, equal days and nights, and assuming we're getting the maximum intensity that we've used before for all 12 hours, which is an overestimate, yes, multiply the value that we just calculated, 3.6, by 12 hours. That's how much you'll get per day maximum, yeah? And then for a year, because it says for the whole year, yeah, 2014, then you multiply by 365 days, again it's an approximation, and you get this much per year, okay? Well, how much is that in compared to what the 2014 value was? So this is in, if we want to change this into terawatts, yeah, energy in terawatts is that much for the year. Yeah, where's that value from? So this is changing this into terawatts, dividing it by the value you can see it's much greater than the 23,800 terawatt hours. Okay, remember, so you can get this into terawatt hours. So it could possibly be, it would easily be possible theoretically. But remember, we've overestimated it. But we've overestimated it by 3 zeros. So it's 1,000 times, at least 1,000 times more than 2014 value. Okay? So that's why the conclusion is it would be possible. Okay? So I've gone into terawatt hours, but if you look at the mark scheme, you can go the other way and work it out into joules. You can compare joules with joules as well. Okay? So anyway, this is a mathematical problem for you to solve. Okay, and we'll have a look at the mark scheme in a minute because we come to the end of the question. And then it says, sandstorms are common in the Sahara Desert. Explain why sandstorms reduce the power generated by the solar panels. Well, the sandstorms will reduce the intensity of light because it will reflect some of it back, yeah, in the opposite direction. So those are the 2 points I would make. You can look at the mark scheme and see where it comes from. Now this also comes from Unit 2. So this is from the IAL paper, Unit 2 question, okay? There it is, Unit 2, January 2020. So this is a normal question, not just for Edexcel linear, but also for the modular as well. Sorry, I'm getting a bit tired. It's now getting a bit late now in the evening. Okay, so there's the mark scheme. You can see how we did the intensity to power conversion and then to energy into joules. And here is all the different comparisons that they made. Yeah, I did this one using 12 hours because obviously you're not going to get sunlight for 24 hours. So I thought the 24-hour one is not a good way of doing it. So as long as you've compared energies, yes, hours with hours or years with years, there's different ways of doing it, okay? So I think I did it right, but I did it a few days ago, so I can't remember exactly the figures on the calculator. I probably should have shown you one more step in between, but you can play with my figures and see if you think I've got them right or wrong. So it's not a long question to finish the exam paper with, but it's 6 marks, and you can see the final bit about the sandstorm. Yes, reduced intensity. Yeah, and then here they're even accepting fewer electrons released by the solar panel because they are semiconductor devices. Now, I don't think they'll be released. They'll be going into the conduction band, and the sandstorm will absorb, block, or reflect some light, which is the points that I would make. I would do this one and this one, okay? And then here it says sandstorm reduces area of the panel or desert. So I think that's one's a bit dubious. I don't think it does. And if they do, I don't know what exactly they mean. And there is the end of this paper. And here is some of the equations they give you for this topic. Yeah. The waves I've crossed out because we didn't use them. And these are all the electricity questions that they give you in the international A-level, because most of the questions I got were from the international A-level paper. So again, once again, if you find these run-throughs useful, don't forget to like them, share them, leave a comment if you have a query, and I can get back to you. And if you want to be a subscriber, you'll be notified when future questions are done. And as we go through the course, I'll be doing some more mechanics questions as well. And then I'll start doing some linear full paper practice ones as well as we're getting ready for our mock exams. Okay, thanks for watching. Bye for now.